Good afternoon. My name is Seunghyun Lee. So today's topic is some dynamic system optimal dedicated lane design for connected vehicles. So that is a content. I will give a simple introduction first and then give us some preliminary ideas for this research. And then I will describe some dynamic traffic assignment considering dedicated lanes for connected vehicles, DS for cars, and numerical studies, and give us some information about concluding remarks. So that is my introduction. So here is my academic journey from South Korea, via Hong Kong, via New Zealand, via Australia, and finally came back to South Korea. So I got the PhD degree in the University of Hong Kong, civil engineering, and then worked at University of Technology Sydney as a lecturer in the School of Computer Science. And currently I'm working at University of Seoul in the Department of Transportation Engineering. There is my majors with hashtag traffic signal control, traffic flow dynamics, artificial intelligence in transportation, corporation ITS, and connected vehicles, public transportation. So today I want to introduce connected autonomous vehicles. As you know, the connected autonomous vehicles have discussed from around 2015 in TRV actively, and yeah, it is quite common research topics for researchers in transportation engineers. So connected vehicles have some ability to employ appropriate control laws and driving patterns to accomplish specific goals, such as maximizing capacity or minimizing travel time via communications between vehicles and infrastructure. So it is very important to understand their potential infrastructure needs and the subsequent impact on the road infrastructure. So dedicated lanes, DLs for cars. DLs have emerged as a widely discussed infrastructure planning and allocation solution for connected vehicles with the mixed traffic flows with the human-driven vehicles, HDVs. So DL's allocation for connected vehicle is only meaningful if it enhances the overall traffic efficiency of the network. So that is some illustration for dedicated lanes for connected vehicles. And this study investigates the advantages of connected vehicles and potential deployment of DLs during the transition phase when connected vehicles with the human-driven vehicles on the same roadway. So there are a lot of discussions from 2017 to 2023. So this study mainly focused on the policy dimension, aiding policymakers in determine the optimal deployment of DLs for connected vehicles to minimize total social costs. So a simple introduction about the researchers. So there are a lot of reports about the DLs for connected vehicles, increasing load capacity and promoting the adoption of connected vehicles from 2016 to 2021. But traffic volume of connected vehicle is low. DLs may not be effective or even decrease the road network efficiency due to its underutilization. It's already dealt with in the two articles. The deployment of the DLs can reduce the number of human-driven vehicles feasible routes and increase their congestion. So there's some studies about DLs for connected vehicles. A lot of studies presented a mathematical framework for integrating DLs for cars into road network to explain the market penetration rate of such a vehicles and route choice. Chen proposed the bi-level programming framework. Also another Chen devises devised the mixed integer bi-level model, and Madani explained some bi-level optimization framework deploying connected vehicle-ready subnetwork for mixed traffic. But in this study, I want to employ some dynamic traffic assignment models to cope with some dynamic different traffic patterns in the mixed traffic. And also there are a lot of studies dealing with some predicted traffic dynamics with a dynamic traffic assignment. So I think everybody knows about the term of dynamic. So dynamic, right? Yeah, someone can answer what is dynamic in transportation engineering, including something, right? In modeling. So I don't know everyone's name. Doyeon? What is dynamic in transportation engineering? Considering something, right? Considering, oh, okay, it's quite near. Yeah, you can find the answer in this, not in this page. Okay, so dynamic means in transportation engineering considering the time variable, so that it is also quite challenging research topics in transportation engineering, considering time varying flow dynamics, time varying demand, time varying some capacity, time varying something like that. So that there are a lot of approaches, including cell transmission models, link transmission models, and two resign transmission models to explain dynamic traffic assignment and dynamic system optimum challenges. So considering dynamic traffic loading and DTA, DSO models for transport network design problem, TNDP, can capture the temporal and spatial propagation of traffic flow. Also, it was used in the design of optimal dedicated bus lanes in this paper, 2021, and wireless charging systems for electric vehicles in two papers. And also, Chakravorty introduced the framework based on LTM, link transmission models, which is used in this research with the DSO model for the optimal configuration of connected vehicles DLs with a multi-lane, multi-class freeway network. While the system optimization assumption may disadvantage some travelers, the DSO model presents the optimal gauge of network infrastructure utilization through diverse network traffic management strategies introduced in this paper. So I think everybody knows about the differences between UE and SO, right? Doyan? What is differences? What is different between UE and SO? You learned UE and SO, right? You can answer in Korean. Okay. So, yeah, anyway, SO optimization assumption may disadvantage some travelers to find their minimized travel times, but we can maximize some kind of social benefit across the total network, so that we can check the effectiveness of the kind of the implementing method, incentive-based travel demand management or traffic control measures, the redistribution of average travel time for vehicles. And also by devising the appropriate pricing control schemes, CARBs can be incentivized to pursue SO routing through toll saving and system-level traffic control measures may become increasingly feasible with the emerging of CARBs, thereby reducing the differences between SO and UE traffic assignment. So there is a research aim. This study aims to fill gaps in the existing literature by devising a link transmission model-based dynamic system optimization framework to ascertain the optimal curve DL design where route choices are considered in a link or in lane within 3M, multi-OD, multi-lane, and multi-class urban network. We extended the single OD, single lane LTM DSO model proposed by co-authors to multi-lane, multi-OD networks in which multiple lanes and vehicle classes allow regular lanes to be utilized for mixed flow of connected vehicles and human-driven vehicles. And we developed MILP, mixed integer linear program, to determine the deployment, timing, and quantity of curved DLs throughout the network. And this proposed approach facilitates the segregation of all or the portion of connected vehicles from human-driven vehicles by allocating a certain number of DLs that optimize the total travel time across the network. And this dynamic approach defines the lane allocation based on the fluctuating penetration rate of connected vehicles along the links. So there is some sets of indices. The transportation network is commonly represented as the directed graph, consisting of nodes and links. So there is some kind of sets, and the major contribution of this research is including the set of classes of vehicles and the set of lanes, and also index for lanes and index for the class of vehicles in here. So there are a lot of parameters. The first one is in the preliminary ideas, we want to find how to define the desired time headway between connected vehicles and connected vehicles and human-driven vehicle, human-driven vehicles and human-driven vehicle, human-driven vehicles and connected vehicle. That is the first stage. And the next stage, we want to find some binary decision variable whether to decide the construction of DLs in each lane, in each link across the network. So DLs for cars are predicted to enhance overall traffic flow and alleviate bottleneck congestion. We assumed that. And also, connected vehicles can be directed to access a set of DLs when available during the specific time period. So we consider two policies. First one is dedicated lanes. Connected vehicles can drive on their DLs while human-driven vehicles in the regular lanes, RLs. All vehicles on the regular lanes behave similar to human-driven vehicles, even they are connected vehicles. And mixed connected vehicles lanes, a portion of connected vehicle can access DLs while the remainder drives on the regular lanes alongside human-driven vehicles. So in the mixed lane, connected vehicles and human-driven vehicles coexist, showing some distinct behavior on the regular lanes, allowing for greater flexibility than the previous policy. Than the dedicated lanes. So this problem, including multi-lane, multi-class 3M, multi-lane, multi-class, multi-OD networks, formulated using dynamic system optimum traffic assignment framework. But in this study, we didn't consider lane changing behaviors or complex maneuvers nearby intersections. And connected vehicles in DLs cannot change lanes within a link. And connected vehicles traveling on regular lanes next to human-driven vehicles cannot switch their lanes to dedicated lanes within a link, but only at the node. And the net benefit of deploying DLs will encourage gradual connected vehicle adoption rather than a sudden surge leading to the gradual increase in the connected vehicle market penetration rates. So we mainly deal with some network transportation network design problem in here with the 3M. So here is some derivatives from car following models to multi-class equilibrium diagram. So triangular equilibrium flow density diagram for mixed connected vehicles, human-driven vehicles traffic flow is derived from the specific car following model for both, for connected vehicles and human-driven vehicles with DLs or without DLs for connected vehicles. So this approach allows us to describe the impact of interactions between connected vehicles and human-driven vehicles in mixed traffic on a link and lane capacity. So it is quite important to consider individual relationship between human-driven vehicles and connected vehicles for the research on the connected vehicles. Even it is some macroscopic analysis, because we need to consider some individual relationship, individual interactions using car following models for these combinations, so that it is quite important part in this research. So these diagrams are specific to each lane and will be employed to establish the time varying lane capacity as a constraint in the DSO problem. So in this study, we used newest car following models due to its simplicity. Yeah, newest car following model is quite simple to convert car following models to triangular equilibrium diagram, so that we can easily generate some triangular flow density fundamental diagram from newest car following model, and that is some equations to explain some locations in the free flow regime and in the congested regime. You can follow some text to understand these equations. It is quite easy equations, right? And then at the equilibrium state, we have some space gap of vehicle J at time t equal SE. And also we can define VJT equal VE for all vehicles. So in free flow regime, we can derive that equations at the equilibrium state to equation 5. In congested regime, we can derive that equations from the previous equations to here, equation 7. It's just a very simple definition using that inverse of K. K means the density, jam density. So inverse of jam density means some minimum space, minimum distance gap between vehicles in a link, so that you can easily derive that equations from the previous equations with the basic concept of traffic flow. So the space gap in the congested state depends on the desired time headway, TJ, which relies on the car following behavior of various vehicle classes for vehicle combinations. The first one is a connected vehicle followed by connected vehicles is a AA type, hence TJ equals TAA. Human-driven vehicles followed by connected vehicles, AH type is a TAH. Connected vehicles followed by human-driven vehicles, HA type is a THA. Human-driven vehicles followed by HDV is a THH. It's easy, right? You follow me? Can you follow me, right? It's easy combinations of human-driven vehicles and connected vehicles. First one is connected vehicle. That is a direction, connected vehicle and connected vehicle. First one. And second one, human-driven vehicle and connected vehicle. Connected vehicle is following human-driven vehicle. And the next one is connected vehicle and human-driven vehicle. Human-driven vehicle is following connected vehicle. And human-driven vehicle and human-driven vehicle is all human-driven vehicles. So human-driven vehicles are unable to communicate with the leading vehicle, we can assume that THA equal THH equal TH. So, yeah, you follow me. Understand that, right? Yeah. And the AH car following type requires a larger desired headway than the AA car following scenario. So connected vehicle can respond more efficiently to the leading vehicle than human. So we can assume that TAA is smaller than TAH is smaller than TH. Yeah, understand that, right? So yeah, it is this concept is used in across all my research, so quite important. So in steady state, the probability p of each car following type occurring is determined as below. A connected vehicle followed by connected vehicles, p is alpha hat. The two vehicles are connected vehicles, alpha hat multiply alpha hat. So that alpha hat square. So you understand that, right? And human-driven vehicle followed by connected vehicle. The probability P is alpha hat times alpha hat 1, 2. So connected vehicle followed by human-driven vehicle, or human-driven vehicle followed by human-driven vehicle, P equal alpha hat 2. So we can estimate the T hat is the mean desired time headway of the mixed traffic using probability P of each car following type occurring. And also we can combine the equations 7 and 8 in the congestion regime to estimate the equilibrium speed in here. The inverse of density is used to define the space gap by utilizing the macroscopic and microscopic relationship, representing as SE equaled inverse of rho minus length of vehicles, where length LV denotes the average length of vehicles. So we can get some very basic equations. Q equal KU, I mean the capacity equals density times velocity, so that we can get these equations from the car following models in here to consider 4 combinations, so that we can estimate some the critical density. We can estimate the critical density and the capacity to illustrate this some aggregate fundamental diagram for mixed connected vehicles and human-driven vehicles. This red line denotes some full human-driven vehicles combinations, so that we can get some maximum capacity around 1,500 vehicle per hour, but we can get some maximum capacity 3,000 for all connected vehicles. So we can use that triangular relationship in each lane, in each link, to calculate some time varied capacity in here. So based on the previous section, we can make some DL policies as follows. The dedicated only lanes policy, we use these equations, QAV, the capacity for connected vehicles for DS, and capacity for human-driven vehicles for the regular lanes, so which is the constant. In this case, there is a clear separation, it is pointed in this page. There is a clear separation between connected vehicles and human-driven vehicles, allowing for the link capacity to be determined as this equation is a simple plus connected vehicle, the capacity for connected vehicles for the capacity for human-driven vehicles, and that L denotes the number of DLs on each link. So in the mixed connected vehicle lane policy, it is a little bit complicated than the only dedicated connected vehicles lane policy. The capacity of the regular lane for mixed connected vehicles and human-driven vehicle traffic is denoted by Q alpha hat. This capacity is a dynamic variable that, considering the different penetration of the connected vehicles on the regular lane, so that we can estimate the capacity of each link Q equal Q connected vehicles plus Q mix. In the Q mix term, we need to consider the probability of the connected vehicles in each link, each link, yes, each link and each lane, so that we can estimate the total capacity in the each link in the equation 16. So we can summarize that information in this page. The mixed class fundamental diagram parameters can be scaled for the multiple lanes on a link with the number of lanes with these equations. L is the number of lanes on each link. We can also get some class aggregated capacity from the equation 18. So you need to remember T hat, I mean the desired time headway for connected vehicles can be less than desired time headway between human-driven vehicles, according to the equation 16. It can be shown that the mixed connected vehicles lane policy describes some higher link capacity compared to the dedicated only lane policy. So finally, we can make some DTA mathematical framework with a binary decision variable. In this model, we aim to determine the deployment and timing and quantity of DS under the DSO framework for 3M, multi-OD, multi-name, multi-class urban network. So BALI indicates the status. I mean, that is the binary decision variable to explain the status of the dedicated lanes L on the link A at the time step I. So we can simplify the dynamic lane specific capacity by multiplying the binary decision variables for each capacity for connected vehicles and the mixed traffic flow vehicles. So also we can make some boundaries for the presence of the human-driven vehicles on each lane. The inflow and outflow vectors of human-driven vehicles must be zero in connected dedicated lanes as follows. And also we can simplify equations 19 and 20 to implement a dedicated only lane policy by substituting QI mix with a Q human-driven vehicles. And if there is a no DS and DS, so the original DSO framework in my co-author's paper can be obtained by using QI equal to Q mix at time I. And also we constructed this linear objective function. The main objective is to maximize total outflow at the destination nodes of the network, while also ensuring the traffic equilibrium and lane capacity limits are satisfied by imposing relevant constraints incorporating the binary decision variables BI. So more specifically, our objective function described in this equation 2021 to maximize the sum of the outflow for each class M at each source node I throughout the entire time horizon T as described in this equation. And also we consider some linear link constraint. It's quite simple concept. We can make some equilibrium between inflow and outflow in each link using these equations. And next one is a node constraint. We also defined these constraints to explain the equilibrium between all inflow and outflow at each node. And also we can define some demand demand equations to define the source and the sink node constraints aimed to load traffic into the network at the origin and release all traffic at the destinations. And the non-holding back problems. If you are studying about the DTA or DSO, you maybe you can heard about the non-holding back problems. We need to handle the non-holding back problems considering reviewers' comments so that we handled these non-holding back problems by maximizing the total incoming flow at any link in this page, in this research, so that we can make some comprehensive MILP framework to implement the optimal deployment of DLs for connected vehicles in a 3M environment. We use the Groby optimization software to solve the MILP framework for problem P. So Groby optimization software is quite useful for optimization method, and you can use some academic free license for your research. So you can search the Groby optimization software for Python. And we applied our method in small-scale single-OD network, detailed illustration to provide detailed illustration of the system's optimal solution, including optimal DL allocation for connected vehicles, and the congestion propagation for various initial penetration levels of connected vehicles at the origin. And also we can check the performance of the proposed method in the large-scale multi-OD network for showcase the computational complexity and the overall improvement achieved by the proposed method and its capability for dealing with large-scale networks. Yeah. So we designed the three scenarios. The first one is our proposed scenario for mixed connected vehicle lanes policy. The optimal DS for connected vehicles are deployed, but the DS are used for mixed connected vehicles and human-driven vehicles. So the second scenario is dedicated only lane policy scenario. The optimal DS for connected vehicles are deployed, but the RLs, regular lanes, are used for human-driven vehicles. That means connected vehicle behave like human-driven vehicles in these regular lanes. And the last scenario is a benchmark case. No DL is deployed and all lanes are used for mixed connected vehicles and human-driven vehicles. So there are some parameters in the table 1. So yeah, each link has 3 lanes, and also the free flow speed is 20 meter per sec, and also there is some reaction time for autonomous vehicles and autonomous vehicles pairs, and also autonomous vehicles and human-driven pairs and human-driven vehicles pairs in here. That is the layout of the single OD network, one origin and one destination, so that we can get that information, implementing the interpret some our binary decision variable to install dedicated lanes in each lane in each link, so that you can follow the horizontal index. The 1 to 1 means the link from node 1 to node 2 in the first lane. So that the first thing is from node 1 to node 2 in this link, the first lane, that is the first in this the horizontal index. So that means we can have all 3 lanes for each link, so that we show the sum. That is the dedicated lanes or dedicated lane or the regular lane in each following the connected vehicles penetration rates. So that for the 100% of the connected vehicles, it's quite easy to understand that we know all lanes should be the dedicated lanes for connected vehicles. And then according to decrease in the penetration rate of connected vehicles, the number of DLs decrease like that. So we can get that information from the proposed mathematical framework. So that is the total performance of the each scenarios. So we can confirm that the scenario 1, the first one, the proposed scenario shows the best performance compared to the scenario 2 and scenario 3. And also we can test some the Q propagation in the link 5, 6. We selected this link. This link is the bottleneck in the simple network, link 5, 6, which was the bottleneck in this research, so that we check the propagation, Q propagation in this link. So in this research, at the 20% of connected vehicles penetration, regular lanes is deployed on lane 1. And the DS for connected vehicles is constructed in lane 2. The regular lane is in lane 3, so that we can confirm that there are less Q propagation in the DS for connected vehicle, but we can check the very heavy congestions in at this time in the regular lanes. That is the for scenario 1, the first scenario. And the second scenario, we can check the heavy congestion levels compared to the previous scenarios in this bottleneck link. And also in this scenario, we can check the DS for connected vehicles is installed in lane 3. In lane 3, there is no any serious congestions across the all analysis time, but in regular lanes, we can check some that kind of congestions in here. For scenario 3, there is a heavy congestion across the all lanes compared to the 2 scenarios. And so we checked some performance of the proposed method in the multi-OD network layout. This network includes 13 nodes, 19 links, and 4 OD pairs. So yeah, is it large network? So yeah, leave your thought. That is quite small network. So they suggested we need to check the performance of the proposed method in larger network, so that I'm learning my computer with 200 nodes and 500 links and 4 OD pairs. Yeah, it is still working in my computer. So yeah, we also checked the performance with the multi-OD network with this regular size network. So the network parameters, links is 23, nodes is 17, and all these OD pairs is 2, and time step duration is 1 minute. So that is the information of the network, so that we can check the performance of the method. So similar to the previous example, the implementation of DS for curve produce higher throughput compared to the base scenario, the last scenario. So, but it is some kind of challenges. Computational performance according to the demand. So the framework's complexity depends on the demand, the number of OD pairs and nodes and links, and the time horizon. So we can check the number of variables, number of constraints can increase linearly according to the increase in demand. But computational time grows dramatically, so that is the kind of very small disadvantage of the proposed method. So there is a conclusion. We make theoretical conclusions to ensure the successful integration of connected vehicles. Appropriate infrastructure must be deployed. The DS for connected vehicles are viewed as an effective strategy to increase overall traffic throughput. A linear optimization framework was proposed in this research to determine optimal DS for connected vehicles in a general 3M environment, multi-lane, multi-OD traffic network, and multi-class under mixed traffic flow. We derived the multi-class fundamental diagram with the dedicated lanes, and also we obtained MILP, mixed integer linear programming formulation that can be efficiently solved by optimization solvers such as Groovy. And we apply the proposed framework to two example network, but in revised manuscript, we applied that framework to three example network. The overall system performance indicator, which involves maximizing the total throughput in the network, determine which legal lanes to convert to DLs for connected vehicles during analysis period. Our numerical results demonstrate that the proposed framework improved overall system performance. And also the method can be utilized to examine the network-wide impact of mixed connected vehicle lanes policy in intensive mixed traffic network. So that is the currently under review in transportation research part E, logistics and transportation reviews. This research includes some kind of complicated mathematical framework so that we submitted that to the logistics. So yeah, currently under review. Yeah, thank you. And that is the some references for this research, and you can read these references for your further study. Yeah, thank you. Yeah, so do you have any questions?
여기 있습니다.
아, 아, 아. Thank you for sharing your interesting research. My question is, have you considered CAV's driving style, such as conservative and aggressive?
Oh,
Yeah.
yeah.
As far as I know, some studies consider conservative CAV driving style. In other words, TAA is larger than TH. So yeah, my question is, have you considered?
Yeah, so in this research, directly we didn't consider some conservative style of the human-driven vehicles. So yeah, it is highly possible to consider that in the for future research. So kind of conservative style of connected vehicles than human-driven vehicles, right? Yeah.
Okay, thank you. And can I ask one more question? Your study spatial scope is grid network, right? So
Sorry.
your study spatial scope is grid network, and I think depending on whether the network is highway or urban network, the result can be significantly different. So your assumption is highway.
Oh, it's not highway. We also consider some intersections with the signal control in here. So that is urban network, grid network in here. Yeah.
Okay, and then have you considered spatial deployment of DLs? Because DL on left side lane or rightmost lane can be significantly
Yeah,
different.
definitely. We considered some locations of the DS on each link in here. So yeah, you can see this graph. We can get some decision binary variable in each lane, such as at the lower level of connected vehicles, we can only apply we can only install the dedicated lanes on the first lane of each link. But in this case, we can install the two lanes of the DLs for connected vehicles at the 60% of penetration rate in here. So that we consider turning flows, we consider some demand from the different directions to different directions in each link.
And did you verify your framework using traffic simulation like VSIM or
Oh, VSIM. No.
only numerical experiment?
numerical
Ah,
example.
okay, I see. Thank you very much.
Yeah.
Thank you for your presentation. I just wanted to clarify myself. If you when you differentiate the conventional cars and autonomous vehicles, is headway is the only variable that you can distinguish
So yeah,
them,
can
or
you more loudly? Speak
sorry,
loudly.
I just wanted to know when you differentiate the conventional cars to the connected vehicles, conventional cars with the connected vehicles, when you differentiate them, is a headway is the only variable to differentiate them, or is the other?
Headway.
Yeah.
Yeah. Good question. Yeah.
Yeah.
In this research, we only consider some desired time headway. Does it differentiate the human-driven vehicles and connected vehicle with a different time headway in here?
So that's the only variable
Yeah.
used
Yeah.
for
Yeah.
this
Yeah.
study.
And reaction time.
Reaction
Yeah.
time.
Reaction
Okay.
time. Yeah.
One more thing. When you do the evaluation, um, I didn't quite understood what would be the evaluation factor to when you do the performance like analysis. Like, do you consider like capacity or increased capacity,
You
or
mean the MOE?
yeah,
MOE. Yeah.
yeah.
In this research, we maximize. Yeah, in this research, we maximize total outflow at the destination nodes of the network in this mathematical framework. So it's kind of, yeah, not capacity. It's kind of saturation, maximizing such a very similar concept of the saturation flow at destination nodes. Yeah.
Thank you.
Yeah.
I'm not doing this kind of research, as you know. This is all about the optimization. But I think a follow up your question. What's your name? Jungin, question. Your assumption. Uh, I think this is very important because if you are a car manufacturer CEO, probably your the gap between the vehicles, you probably make a very even longer distance than human vehicle, because you don't want to get any accident. You build the autonomous vehicle, but you get an accident, then your company might collapse. So in the beginning, very beginning, like I say, these guys might be has a much longer distance between. Okay, so the assumption here is skeptical
Yeah,
sometimes.
that's right.
So
Yeah.
my question is, if you write a paper, this kind of paper, and submit it to that kind of journal, do you also expect some critics from the reviewers on this issue? Or you
Yeah, I remember. Yeah,
ready to get those kind of
yeah.
comments? And
I remember that comment from the reviewers about the concept of connected vehicles considering in this research. So we tackled that reviewers comment with some complexity of mathematical framework in this research. So we want to simplify the connected vehicle problems with the linear problems, and also to get some more information of the network, to optimize more information of network to with the simplified concept of vehicles and simplified some mathematical framework in here. So normally we use some nonlinear relationship between vehicles in here, between the connected vehicle and human-driven vehicle, connected vehicle, or human-driven vehicles. We normally use the nonlinear relationship for macroscopic or microscopic flow analysis. But in here, we want to simplify the relationship between them for kind of macroscopic some optimization. Yeah.
Okay, then in a big picture,
Yeah, that's right.
why do we need this kind of research?
Yeah, in big picture, we want to help decision makers to decide whether DS for connected vehicles is installed in specific lanes or not, or in specific some routes, specific links or not. Yeah, that is the final some contribution of this research in practical views.
So it can be used for transport planning.
Yeah, that's right.
Okay. Yeah. Yeah. Any more questions? Yeah.
I'm actually working on planning.
Planning,
So I'm working on the traffic demand modeling.
demand modeling.
So I'm trying to find a way how I can analyze the autonomous vehicles. Because the model right now we have is only for the human-driven behavior or like conventional cars. So like, what do you think? What other factors could we uh, incorporate other than headway to?
Other than headway,
Yeah,
in at the planning level,
yeah,
kind of traffic assignment
yeah.
or mode choice, street distribution like that, right? So reaction time also related to time headway, right? And what else? Oh, the connected vehicle can be more efficient to find their optimal routes than human-driven vehicles because connected means we can communicate the information about some traffic status or some emergency situation at each link to with the communicating with some following vehicles, and then the information can transfer from one vehicle and next vehicle and next vehicle. So connected vehicle can find more efficiently their optimal routes than human-driven vehicles. It's just an idea.
Okay,
Yeah, it could be possible, I think.
okay. Thank you.
Yeah, route choice
Yeah.
or yeah. In traffic assignment, we need to make some other class like this research. The vehicles, including the specific class in your research, can find can find their optimal routes with the real-time information or the information before a few seconds so that they can find some. Yeah, and also in this research, we propose I mean, the system optimum method in here. So system optimization is the purpose of transportation engineers. But for users, we want to minimize our marginal cost, marginal travel time for individuals. But from the perspective of transportation planners, we want to maximize system, maximize system benefits, rather than minimizing user cost, right? So that you can apply that kind of concepts of the partially of the system optimization on some your planning problems. That is just idea. Yeah.
Okay. Just one more thing. When you set the headway values for the categories that you just set, is there a specific reason for setting the values like 1.5 or
Oh,
like
no,
no?
there is no any specific reason, just so we follow the researchers.
Okay.
Yeah.
Thank you.
Thank you.
Uh, are you planning to consider lane change behavior?
Lane changing behavior, yes. We need to consider lane changing behavior because it is really realistic to consider lane changing behavior in here, right?
Yeah.
So yeah, I should.
And you said this network is urban network, right? So there are many intersections here. And uh, how uh, how can vehicles turn left or turn right when they are using dedicated lanes?
Depending on their,
For
you mean
example,
the
yeah.
dedicated lane?
I
It's
mean,
like a bus dedicated lanes
for
that they
example,
can.
uh, in the case of first lane is being dedicated lanes, uh, vehicle using that lane, and they want to when they want to turn right. I mean, turn right at the
Yeah, yeah,
intersection.
yeah.
How can vehicle do that?
So in this research, we didn't check that kind of very some microscopic behavior of the vehicle
Ah,
at the
okay,
intersection.
okay.
But I think, yeah, mm, they can change their, they can turn left or right in the process of optimization. I think, yeah.
Okay, I see. Thank you.
Yeah.
Thank you for sharing your work. And I think a platooning technology can be a virtual moving dedicated lane. So have you discussed this kind of concept and or
Oh,
plan to?
yeah, very good comment. So yeah, platooning strategy is also quite important. But in this research, I just illustrate the connected vehicle problems with more some macroscopic views. But for platooning strategy could be handled from the kind of some microscopic views. So that yeah, it is quite good comments for future research. Yeah, good.
Oh, I think we once worked together at the University of Seoul. Yes. I have a comment for maybe future studies. I just read a little bit around this CAV, connected vehicle movement on the road, and platooning. And I understood that the movement of these vehicles can have a lot of impact on infrastructure. So looking at the main focus of the study, basically you want to look at improving the efficiency of the whole transport system in case we have the connected vehicles. And you are actually trying to determine the efficiency based on the throughput of the whole system. But then looking at the impact that these vehicles can have on the system, actually when they are moving together with the human-driven vehicles, I think that in the future, if we can actually, how do I say this, capture the impact of how these vehicles can actually affect the whole movement of the vehicles, particularly at the intersections. We can actually measure the real world effect of these things and also look at the potential efficiency that we can get. Is it going to be more efficient or actually going to reduce the whole efficiency of the system in terms of throughput? So basically, I'm just suggesting this as a future study area that maybe you want to look at.
Yeah, good. Thank you.
Maybe I've got a very last question. Why do you like this kind of research?
Oh, this research. Just
A lot of romance. I know it looks sexy, okay, but when it comes to implementation in real life, to how much extent can you implement your theory,
yeah. So yeah,
contribution
yeah,
to the practice?
yeah. To be honest, this research is for research. Yeah. Just using complex mathematics and complicated concepts and yeah. Research for research.
Very yes. I think that's I think Netherlands probably really the students, it's just where you sometimes write a paper for paper, okay, but it happens. And Seunghyun published a lot of papers in top journals, in particular transport engineering, okay. Although it's very high quality theoretical contributions in it. Again, it sometimes is hard to implement it, but still, I believe it still have a value in the academic world, because I think that's the steam and it trigger the curiosity in this area by formulating the equations altogether. So some of you guys may be interested in mathematics, then this kind of papers would be very, very good. Okay, yeah. End of the seminar. Again, it's thanks to the Seunghyun Lee today, and thank you for coming to the seminar today.